Hello everyone, this is Olivia. In this video, I will go over tutorial 3A, which uses the sentiment lexicon from Liu and Hu, and to do unsupervised sentiment classification, and then also some supervised sentiment classification that uses this lexicon. This is building on the concepts of how sentiment lexicon can be used for these two types of purposes in the previous video on sentiment lexicon, the lecture video. Okay, so let's get to that. The beginning part is similar, just in loading up some of the packages, and we're using movie1.csv again, and setting working directory, and start to read the file and transform label. Take a look at transform the text coding scheme, and this is a very typical first block, first code chunk. So I already ran it before, so I'm not gonna run it. As I mentioned in the video or in the slides on sentiment lexicon, that there is a very popular sentiment lexicon by Hu and Liu. There are lots of papers by them, and their co-authors have, and many others have used this. So there are additional citations that you can find, and many text mining data scientists and researchers out there have used very similar code chunk that uses this sentiment lexicon that must have originated from these authors. But the particular code chunk that I used were from the sample code in chapter 3 of the reference data mining applications with R. As I mentioned, you can find code and data sets used in this book in their website, and the book itself is available through the library. You can view content digitally. So the first part is about using this sentiment lexicon to come up with sentiment scores, which will basically be the net scores of how many positive sentiment word counts minus negative sentiment word occurrence counts. Actually, the same word can appear multiple times. Each time it appears can be counted multiple times. And I think here is more of a word count. So it's the code itself. You don't have to recode it. It has been modified for this tutorial a little bit, but overall the structure is very similar. So it defines a function that will return the score, or numerical score, for each record that is included in this corpus. So it will start out with a corpus like our movie reviews corpus, and so this is a whole corpus, and we'll take the lexicons, the positive and negative sentiment lexicons in two sets. Function has progress bars. You can not include it, or you can indicate none here, so that progress bar will not be printed when you need uh, the R script that includes this type of function. So there are a couple packages to divide up or split and apply functions to lists or vectors and to text. And inside this function, essentially it will use a type of command called LA applet. So it's a little bit different from LA apply. And it will take an array, split it up, and apply function to it. So there is essentially, you can think of this as an array of text. Inside this function, which starts from here and ends just here, will split up this array into single row or single element in the array. So the single element of this array is called sentence. So inside this bracket, it will apply a function to each of these sentences. Again, positive words and negative words lexicons will be used. And I should also mention that I think I went a little bit further down too fast, that these positive words and negative words were words in this file, positive words.txt and negative words.txt, that were made available by this data scientists, and they're also in our file folder for you to use. So you have to have this in your working directory to first use scan commands. If you didn't use this before, it actually has a lot of nice options to handle text input. And this was further combined, use the combine functions to be sure that these are in the list forms that are required by this function. So these are nested functions, function for the whole corpus and the function for individual text document in the corpus. So this will be our reviews. This is a single review. So inside single review is text processing, very similar to using TM map. This one uses use this general substitute function to handle, because this has been used in with Twitter data in chapter 3 of the of data mining applications with R. So there are some regular expression type of text or content that uses different kind of commands. So this just clean up punctuation, control digits and numbers, and transform to lowercase. This is from TM, or this is common to several packages. And then, so each review has gone through this cleaning, and but before we will start to look up the words, we first need to split up the words. So this again is for regular expression, and to split a text document into a list of words. So the words in this list are the same as this, but we use several data scientists use this type of unlist to make sure that the data structure that contains these words will work with functions that match or others that uses a list. We use it from time to time, sometimes without the data structure is in the right list, but sometimes it may be list nested in list and nested in list. So it has worked for us in some other tutorial code as well, or the later part of it. So this one, this word list is a list of words from each document, and this code is for one document at a time. So now we start to take the words, compare them to positive words in the positive sentiment lexicon using match function. So this match function is very convenient. It will identify the words, the position in this word list that matches with words in this. And so like amazing in both will be identified. The index will be indicated in this result list is also a list of matched words using the positive sentiment lexicon. This similarly gives you a list of matched negative words in the negative sentiment lexicon. This negative negation of missing, it will remove missing elements and just clean up positive matches and negative matches with only matched words. Then when a function sum is applied to each of these two lists, it will give you counts of the number of matches. And so the subtracting negative matches from positive matches will give you the difference between the two, and that difference is the sentiment score that a lot of data scientists and that we, like a lot of data scientists, we will practice using to do sentiment scoring or sentiment classification. So the score will be output from this function for each document, and this will be applied to each document, and then to complete sentiment scoring. So the output of the first function scores a data frame that contains scores for scores and sentences. So this only defines, we won't run it because we will first get the reviews ready and then start running it. Like I said before, that when I ran it with our list of reviews directly from the review column of movie, of the reviews, the review column in movie1.csv, it was giving me some errors. So same thing, I unlist this to the level that it could work with this sentiment score sentiment function that was just previously defined, which is the function name, the function output. Okay, so we can run it now. So to get started, this is the one that calls the function to generate score.sentiment for our corpus. So this is our corpus, and using positive, negative word sentiment lexicon. And when we call it to be consistent, progress bar is set to be none, so no progress bar will be generated when the function is being executed. Otherwise, in the original code, you will see bar, which is very nice, but in the Word doc of the results is a pain to see many pages of them. Okay, so we can run this, and it takes a little bit time, but not that long. Okay, then after we have the score, then this command is used to take the score column of this data frame, assign it back to our original data frame that contains the movie reviews and the original label. And inside, the new column name is called positive negative score. So essentially the score we generate using the lexicon. So let's run that. It's real quick. Let's just take a look at 10 of them. I didn't generate very pretty printout. Just want to show the true labels for the first 10. I think there's some sorting, so all of them are 1 means negative, and the score that been generated for negative, some of them are actually have net positive sentiment score, and this after and there are more negative sentiment scores than positive sentiment score. So this is the net score, so it's negative. And some of the common approaches is just use 0 as a threshold to divide up If you only want two sentiment classes, positive and negative, and we can use a simple approach to be, say, positive to be positive sentiments and negative score to be negative sentiment. Out of this 10, you can see 3 of them will actually be 2, because 2 is positive, 1 is negative if we use this rule, and 7 of them will be negative. This is actually very representative. So it's about the accuracy of this unsupervised approach that uses sentiment lexicon will give you out of these 10 records 70% accuracy rate. Even though it's unsupervised, because we actually have the original positive, negative sentiment labels in this data set, so we can conveniently evaluate how good is this unsupervised approach, how good this approach is. And so this is just only 10. So let's use this approach to start doing sentiment classification. And one thing is we have to decide whether when the score is 0, meaning the positive matches and the negative matches, word matches in review are exactly the same, like 3 and 3, so, and 5 and 5, 10 and 10. So as a result, the sentiment score end up to be 0. We have to decide whether we put 0 as negative or 0 as positive. And for this particular data set and most of the applications, it seems like they it hasn't made a huge difference. Negative is a little bit better, and we'll try both really quick. So in order to change from score positive to be positive sentiment, negative to be negative sentiment, we use if else. And so if this expression is true, then the output of this function will be positive. Otherwise, it will be negative. So if it's entirely positive, the label to go into, which will be added to each movie review, review I in this for loop. And it's a little bit longish name. Just means the score is, the class is generated using sentiment score. And that 0 is considered negative, 0 negative. Okay. So this is a for loop for each of the reviews from up to the last review. And we will do this if else statement and to generate positive and negative labels or classification, but using a rule approach. So we're not building model, we're not training any model, we're just using this rule. And we're taking the entire file in this loop to do this. So, and I think we can run this whole chunk together. Let me just, afterwards, because this will give possibly only character string, so I want to make sure that when I use confusion metrics or calculate the true accuracy rate, true positive rate, and or recall rate and precision rate, and F measures that the labels have the right data type, which has to be a factor type. So I just do this, and after this, even though there are no models, no classification models that are used, but as long as we have the predicted or rule-based label sentiment class and the original label of the sentiments, and we define positive to be positive, we can still generate confusion metrics, and similarly we can still generate other classification metrics. So let me run this chunk. It won't take very long because it's only rule-based. So as I mentioned, that the first 10 records are kind of indicative of the whole file. We're taking 2,000, not just 1,000 in the train, or 500 in test 1 or 500 in test 2. Taking the whole 2,000 reviews in movie 1 and this is the confusion matrix and confusion metrics, and then these are true positive and true negative for different classes, which we can see also similarly the true the precision of this and the precision of this are here, and the overall accuracy is this, and very similar to our first-hand records. The next one is just same, very similar code, but here we treat 0 as positive. So very similar code, and except that at the end, we just take a look at about 12 records that have zeros in them to see the comparison of the different rule-based sentiment classes that we have generated. So this is the code ran to put 0 into the positive class. And here we generate confusion metrics, and the accuracy rate and the F measures of the two classes are overall accuracy and F measures of the two classes, just slightly lower by about 0.5 compared to treating 0 as negative. And here we got 12 records. Here the actual score is 0, another one 0. Positive definitely would generate 2, which means positive classes no matter what. And negative, the others will definitely generate 1 no matter which rule. Except for 0, then treating 0 as negative will give you 1. Treating 0 as positive will give you 2. So that's this two different. That's the difference. Okay, so now we have finished unsupervised classification, and we check out the performance. So I asked you to think about a few questions. We've been using the same file in supervised sentiment classification in tutorial 1 and tutorials 2A and 2B. And so if you remember, compare this about 70% accuracy to other earlier supervised sentiment classification. How are they, how is this performance better or worse? So instead of going back to the tutorial output, I think recently if you have been running tutorial 2, you could remember that from using 95% sparsity, and the performance have been SVM classifier can classify more than 80%. But decision tree sometimes still lower than 70%. So it's better than some and worse than some. So depends on whether you have the option to do supervised or you want to combine unsupervised and supervised. It's good for you to check whenever you can the performance of unsupervised labeling, so you know what's the possible the percentage of times that when you may make an error in this lexicon-based classification labeling. Okay, the next question is, I have used the whole set of reviews, the whole corpus, without splitting into train test 1 and test 2 to generate the confusion, to generate sentiment labels, positive and negative, using the lexicon words, and also to generate performance evaluation using confusion metrics and using M metric. And was there a problem with that? And the answer is related to whether the classification labels or the estimated labels are learned from data, generated using a model that learned from data or not. And when we learn from data, it means that we're training a model, and then in order to correctly evaluate the model performance, we want to make sure we train model on data and not to reuse the data that you use to train the model when you test it. Here, we're not training a model. We're not, the positive and negative labels were not data-driven, at least not driven by this data set. It is based on lexicon words. So it's not driven by the corpus, but it is driven by a set of words, essentially are set of patterns or set of rules. So this is something that you oftentimes should think about when you need to split data or separate training and testing, is when you are training a model by learning the model from data, in this case from textual documents. Last question is, now we have done unsupervised learning, and now it's time to ask, instead of only using this lexicon to do unsupervised learning the way that we have seen so far, can we also use it in some way where bag of words were used for supervised learning? And obviously the answer is yes, as we hinted, we talked about in the sentiment lexicon lecture, that we could use these words to filter bag of words or to generate bag of words, either at the feature extraction phase or the feature reduction phase. Obviously, it's good to reduce the number of features right at the beginning. So during feature extraction, we can use this to reduce the number of features. Okay, so now we are going to start using lexicon in ways similar to the generation, in ways that are required for supervised sentiment classification. So since it's supervised, we will train model in order to avoid using training data also in the testing data. So now we have to split the data. And this chunk of code is the same as the last few tutorials, and I already ran it before, so I don't have to run it. So there's train, test 1, test 2, 50%, 25%, 25% split. Now, before we can start using the positive words and negative words lexicon to help us extract word features from this movie one corpus, I will do a little bit of processing of the word list. First, I don't want to do this separately, so I will combine them together. And I'm reusing this variable name. So from now on, this set of words are the original, this list, pn.words, combine these two lists. And so we can run this and just do that. If you want to take a look, we can take a look. It will just do one list before the other. And then there may be duplicates, so we use this function duplicated to check if as long as there's any, it will return true. And the answer is true. So we should think about removing it. Before removing it, I will first check on how many, and so give me a sense of how many were removed. So this unique will remove anything that's not unique and keep the unique ones. And afterwards, we just remove only 3. So no biggie, not a big deal. When I ran this list, I was getting error about this word, which is in this row. So we want to look it up, and if this is a little bit manual, it's after the fact I come back to fix the code. in the future, we can, to scale it up, we can think about filtering out other special character using TM. But right now, I just first look up, found it, and remove it. So negative found. So whatever we found using the same match, given this one is what I want to look up, and once it's found, we remove it from PN words. And if we check it, now we see that words, our length is shorter. So this also gives you a sense of the total number of words. About 2/3 of this are negative words, and one third is positive words. Then after that, now for the 3 data set, train, test 1, and test 2, they need to go through some sort of processing to make sure that we are matching we're comparing apple in the movie reviews to apples in the lexicon. So for example, all words are lowercase, so I just want to make sure we do lowercase. The others I'm not too worried about because we're doing matching. So even if they're punctuations or numerical digits, the matches will automatically just only focus on the words in this lexicon. So I only included transformation to lower, and sometimes lower will give us problem, depends on your R's version, and content transformer can help make sure this can be compatible with more versions of R. And so since now we're back to doing supervised learning, and I will continue the approaches of using term weights, using weights like like term frequency, TF, or binary occurrence, or term presence, or TF-IDF. And here I just use TF of the words. That is a combination of the word. It is basically the words that in the sentiment lexicon that can be found in the reviews, and any of the reviews. And then we will keep the word, and we will use the word to create document term metrics. And the value of the word, we're not using difference between the counts of total, because the weight has to be, value has to be for a term, so we use term frequency. So the important thing is, in the past, when we generate document term metrics for trained data, we usually, this is the process where we are identifying backup words for also test 1 and test 2 data set. But this time, the words that were from the lexicon after some cleaning is, will be the fixed list of words that we use to generate document term metrics. So they will go into the columns, and the term frequency will be counting how often the word appear in each of the document. So, so even for trained document term metrics, we will need to use this option in list. Dictionary equals to this set of words, the words in this list. And we just take step 6 came out of the TM function to generate this. And I think I have performed this. It won't take too long, but let's just keep going because I already have this in the environment, and we can still do this. I think we don't need to check dimension to find out how many words. Essentially, the number of words will be what was in this list. For this, the number of columns in this document term matrix will be the same as the length of this list of lexicon words. And but we do want to 6,785 is a lot of words, and when we do classification, can be very noisy. It may be and also take a long time. So we can combine with some other feature reduction, such as sparse term removal. So just to remove any of these words that don't appear, that only keep the words that appear in 5% or more of the reviews. So afterwards, then from 6,785, the number of words remain in 5% or more of the 2,000 movie reviews. I'm sorry, 1,000 movie reviews in train data is only 156. So this actually will be, after filtering, now we have to recreate and reset the bag of words that will be used throughout the rest of the document term matrix generation. So this bag of words is called positive, negative lexicon, bag of word, and 95 sparsity. And what this term matrix, document term matrix, that is generated using this remove sparse terms will be the input here to generate this set of bag of words. And I already ran that before, so let's take a look at the set of bag of words. So only 156 of them, and not much of no stemming and no, yeah, that's one thing I should mention is the words had no stemming actually has misspells, and so those are carefully selected words, and that can still be found in 5% or more of the, at least 5% of the training data set. So we can continue this for the rest of, for test 1 and test 2 using this. Now, when we generate the document term matrix for test 1, and we call this document term matrix 95 sparsity using positive negative words in conjunction with this 95 sparsity. And we do similar processing on test 1, and the dictionary now use this combined this sparsity filter positive negative words, and the rest are very similar to earlier tutorial, and I already ran them, so we don't need to run this set of our commands. So now we have finished generating the document term matrices for train, for test 1 and test 2. And so now we can do sentiment classification. And what I didn't show is that it also did the data frame that combined sentiment labels back with the document term matrix to create test 2, test 1, and train input data files to this set of sentiment classification commands. So this is the train data input file, and this is the test 1 input file, test 2 input file for doing C3 model training, testing, evaluation using test 1, testing and evaluation using test 2. The next are naive Bayesian, and then SVM. And this with 156 columns, this actually runs pretty quick, much quicker than before. And we can start to see that the performance of C3s are similar to others, and so that kind of reduction hasn't hurt very much. And naive Bayesians and also look pretty reasonable, 75 and 72. And SVMs are not as good as the best, of over 80 or 80% or 82%, but it's also not too bad. So if we have labels and also have a lexicon, this has the advantage of still giving good performance. And as you can see, that with 156 columns, the performance is actually good, and it runs also fast enough. So this is actually, this is one approach. Let's start to think about some question now. We talk about comparing the results. The results the performance look reasonable, and if we have fewer features, and the features are pretty good because these are words carefully selected into a lexicon. So it seems like it has given this corpus good sentiment classification power. So the next question is, what are the other ways to improve sentiment classification using PN words? Do we always have to use sparsity with the sentiment words, or can we do it somewhat differently? So the idea is, well, how about we, instead of using sparsity to reduce the from 6,875 or 6,758 or 85 words to 156, can we use some other ways to do dimension reduction? And remember last time we in tutorial 2B we started to use F selector, and which includes a wide range of feature selection functions that you can use. And because of decision trees, I think most students are most familiar with information gain. So I will just only use information gain here, and just for comparison. And I think it's an interesting comparison. I will point out what happened if we essentially the performance is not as good this way, but the reason why. So in the next chunk, I will not do sparsity. I will go back to the document term metrics that we had created for train and for test 1 and for test 2 separately, for train, and then create the input file for train. But the test 1 document term metrics earlier on was created using the backup words selected filter using sparsity. So now I don't want to use sparsity, so I want to keep the original dictionary of this PN sentiment lexicon, and recreate the document term metrics for text 1, and create input file by combining this document term metrics with the original sentiment label. I'll do the same for test 2. And I already ran this, so we have now the input file that we can and document term metrics that we can use for feature selection. So for feature selection, we need input file and the label. So we will select features using trained data and then test it and reduce it in the testing sets as well. So because now, if you remember, in this data set, the number of columns are almost 6,800 of them. So information gain, to calculate the information gain for each of the columns and store them in this way will take a long time. So I already ran it, and I won't do it again. And here, I won't run it here. And I use cutoff K to reduce the set of features from 6,000, almost 6,800 to only 175. And that will be the IG subset. And since I already ran it, we can take a look at what is in IG subset. Oh, sorry, actually I need to, I probably need to rerun it. Let me see. Actually, it should be 125 instead of 175 because we only have because we only have 156 words earlier on, so I want to reduce it only to about 125. So let's see what happened. I'm kind of running this on the fly, and you can see this is from this is 125 features selected from sentiment lexicons, not being filtered by 95% sparsity, and so this is the set of words that we could see. And so now I changed this. So I'm going to recreate the train input file, test 1 input file, test 2 input file for sentiment classification based on the IG subset. That's the words stored here, and filter out the rest of the train and test 1, test 2 data set in the document term metrics and combine them with the original label. So this will be the data set to go into sentiment classification. So now we're using 125 here and 125 here. And let's see what happened. And this is this very same kind of code for sentiment classification using C-tree, naive Bayesian, and SVM. And the input data set was built using positive, negative sentiment lexicon words and information games feature selection. So it shouldn't take too long. So let's run it, and we can see the result. The performance is for decision tree very similar to the 95 sparsity ones, and now we're into naive Bayesian, and naive Bayesian has had also fairly dropped a little bit to 73. Early on it has somewhat of a 75, but 73 very steady, and then SVM has a widespread of this too, and I think the features are maybe fairly similar to the earlier round that I ran. Okay, so that may be the reason. Now let's just do this one more time and change the cutoff to 25, so we have an even smaller set of feature, very small, only 25, and then run the sentiment classification. So let's do that. Get the data set prepared, and let's run the sentiment classification using these 3 classifiers, and using 25 features only. SVM dropped quite a bit here by 5 also, but the other test 2 data set didn't drop that much. And naive Bayesian very good with only 25. Decision tree didn't change very much at all. And they oftentimes have the same accuracy, but still different F measures. Just I always have to double check whether it was the same data set and so on. So last but not the least, I do want to quickly just mention that approach was just to see, because last week we talked about, oh no, if we want to do feature selection, how about we throw a lot of features and let feature selection like information game to select out of a lot instead of 1,000, instead of out of 600. And now we're selecting out of 6,000 or 7,000. Sometimes it works, sometimes it doesn't. And in fact, earlier on when I used 175 features, and the result was not as good. So if you want, you can do a combination. You can use the positive and negative words as your initial dictionary to select backup words. You can use 95% sparsity to first filter them down, and then in this case, it will filter it down to about say 160 some 65 terms. Then you can do additional information gain to rank order them or feature selection. If you want to do that, then you can also do that. And so this is actually really quick. So even though it has information gain, after I have already filtered down to a small number of features, we can see that this information gain function can run much faster than before. And so, and that which I didn't run last time. And now using this 125, and again to run, we can see the feature set are pretty much similar. So, and the code is included that you can keep test. You can also test run them. That's all for tutorial 3A about different uses of sentiment lexicon from the from Liu and Hu. Bye.